Ready. First of all, tomorrow morning please bring the PC in room 0.5 and we will dedicate the whole morning, 2 hours, to learning how to use the software that I mentioned to you last time. So just tomorrow, introduction to the software. I just want to inform you, because as I said, you are not strictly required to attend these exercises, and so you can know, in advance what I'm doing. Today, instead, I will speak for 3 hours, with a break of 15 minutes after 1 hour and a half, around quarter to 11. And I will, first of all, continue with the introduction to the course, and I will start with some more quantitative treatment today, and then in the last hour, probably more than 1 hour, I will present to you a case study. So the last hour, probably more, will be descriptive, let's say, because I need to introduce a case study in order to clarify what is the context, the typical context in which we develop our consultancy activity, our research activity. Okay, now, you may remember that on Monday I started talking on the total availability of water over the Earth, and I also said that this is a static representation. I told you to make a difference between what are the water reservoirs and what are the cases, the water bodies in which you have water flowing, because it's a different context. Of course, if you have a huge reservoir of water, it could be very huge, but if it is not renewable water, then you have to be very careful to use it, because once that you used it, it's depleted, it's exhausted. If you have instead a water body where water is flowing, maybe that you have a very limited volume, but this volume is renewed. So it means that you are less concerned to use it. So you have to always make this difference when you deal with water between renewable resources and not renewable resources. It's an important difference because, for obvious reason, when you use a resource that is renewable, you are less concerned. It's like when you plan to use petrol rather than solar energy to produce energy. It's a big difference. Solar energy is something that is renewed. The petrol is not renewable, or let's say at least it's renewable in times that are so long that we consider it not renewable. And the same for water. In some cases you have static storages, not renewable. In other cases you have water flowing very quickly, which means that the renewal time is short. In other cases you have intermediate situations where the renewal time is long. So if you think, for instance, at river and groundwater, they are both renewable in principle, but with the difference that a river is renewed very quickly. Groundwater takes a longer time. And therefore, this is an important variable, the renewable time of a water resource. It's something that you always have to consider in your decision. Now, what is the reason, you may wonder, why I started introducing an assessment of water quantity? And also I mentioned to you, if I remember on Monday, that the first part of our subject, of our lectures, will be dedicated to water availability assessment. So, why this? Because, as I said, this is an important problem. And I just would like now to make an introduction to put the problem into context, to clarify for what reason, also from a mathematical point of view, we need to estimate water resources availability. And let me say that all the problems of water resources management, grazie, all the problems related to water resources management basically can be solved by applying a very simple equation, which I am introducing now, which is the equation of the water balance. You could call it a mass balance equation. You could call it the continuity equation, as it's called in Italian, equazione di continuità, we say in Italy. And with this very simple equation that I am introducing, you can solve every problem related to water resources management. And you know that in order to solve an equation, you need to specify some unknowns of the equations. You need to specify.
Sorry, scusa. Questa qui lo riuscite a chiudere, questa qui non si chiude.
Non si chiude, ho capito.
Al limite poi si tira un po' la tenda.
Sì, magari tiriamo un pochino la tenda, ma sì, così trovate
Sì, la tenda tocca lì, guarda.
Ah, ho capito.
Tocca tutto, quindi quello per scala alta.
Va bene, ok, perfetto, la ringrazio.
Grazie.
Ma no, è anche più troppo, aspetta, se no non ci vediamo più. Grazie. Le due mani scegliamo quello migliore. Grazie mille. Do we have enough light in this way? Okay, otherwise, just let me know, I can move a bit. And you know, if it is cool, it's better because you don't feel asleep on the other end, you know. Sorry for this. And of course, it's a problem that could be solved with a long stay, and I told him not to solve it now, because otherwise we have to break the lecture for about quarter of an hour, and I hope it's not too cool. If you feel uncomfortable, just let me know. Okay, so as I said, there is a very simple equation, which is the water balance equation, that allows us to solve all our water resources management problems. I said that in any equation we have unknowns, and the water resources availability is one unknown of this equation. So let me introduce the equation. And in a very general form, be careful, it's very simple in principle. Because as I told you, water resources management problems, usually, from a theoretical point of view, are simple problems. So don't be concerned by the fact that the equation is very simple. The water balance equation, first of all, let me go back. First of all, the water balance equation should be applied to a volume of space, which we call the control volume. And I will define better the control volume later on. For now, let's say that you need to consider a volume in space that can be fixed or moving, where you want to apply the water balance equation. And let me make it a very simple example. Let's suppose that you are interested in using the water from a lake. Your control volume is the lake itself, because you need to make the water balance for the lake. Or, if you refer to a glass of water, the same thing. Your control volume is the glass of water. It's a volume in space, the control volume, to which you refer to. And with reference to this volume in space, the water balance equation says that if you call with P as a function of time, the input to the volume, the water input to the volume, typically in many of our applications, this P is rainfall. And I call it P because in Italian it's called pioggia, and therefore we use in Italy P. In an international context you could find R, rainfall, doesn't matter. Let's call it P. It is the input. And this is a flux, meaning volume of water per unit time entering into the control volume. So let me, if I wanted to put a dimension to it, let me put L squared, where L is a distance for me, length divided by time. This is the dimension of this input, okay? Then, this is the input to the volume, then we have to subtract the output from the volume. This is output. Again, the dimension is L squared divided by time.
LQ, not L squared.
Sorry?
LQ.
Oh yeah, sorry, cube.
No.
Sorry for that. I said square, you know. I'm doing my best in English, but... and thank you for pointing it out. Okay? And then we have the losses. Usually we call them E. Losses. again, L cube divided by time. What are the losses? The losses could be, for instance, evaporation. This is why I used E as a symbol. But there might be other losses. Evaporation is the most simple to introduce. Okay, so you have an input minus two outputs, which are equal to what? To the change in time of the water storage. W is storage. And the dimension is L cube. The water storage in the control volume. W is the water storage in the control volume. Again, I write here, this is the water balance equation, also called continuity equation. What is this equation from a physical point of view? It is, as I already mentioned to you, a mass balance equation, which refers to the mass of water. It's because, you know, basically, this is a balance of volumes. You see, this is a balance of volumes because there is a flux of volume entering into it. There is a flux of volume exiting from the control volume, a flux of losses, and which is equated to a change in volume of water storage. So this is a volume equation. So you may ask me, why do you call it mass balance equation and not volume balance equation? Let's make clear that if the mass density doesn't change, again, if the mass density doesn't change, a volume balance equation has the same meaning of a mass balance equation. And another important premise, in water resources management, we always consider, apart from very specific cases, that the mass density of water is constant. I say again, in water resources management, apart from very specific cases, which we don't consider in the subject, we will always assume that the mass density of water is constant, which means that water is incompressible. Is this clear to you? And therefore, I can say that this is a mass balance equation. Just to make you, just to give you some more details, in general, water is compressible, but you need a very high pressure to compress it. To change the mass density of water is possible, but you need very high pressures. So only in very specific cases in operational engineering you may deal with situations in which water is compressed, and these are always very delicate situations. And if you had some background in hydraulics, you may remember what is water hammer, or colpo d'ariete in Italian. And this is a case in which, when you have the water hammer, it's a case in which you have a phenomena that is induced by the fact that the mass density of water is changed. But these are, as I said, very specific situations which we don't consider here, because we don't design pipes to provide water to people. We just focus on policies. Or if we design something, we don't go to the level of detail of pipes and hydropower plants. So in our subject here, as I said, we always assume that the mass density of water is constant, and therefore the volume equation is equivalent to a mass balance equation. Another question that you may have, I try to stimulate your curiosity, is why I spent 5 minutes talking on the equivalence of the mass balance equation with the volume equation. You could say, why did you mention it? You could refer to a volume equation and that's it. Okay? No, I think it's important that I highlight that I'm dealing with a mass balance equation because, you know, if I forgot this, I could have called this volume equation. But I think it's very important that I highlight and I put to your attention that this is a mass balance equation. Why this? Because, you know, when you deal with science, and hydrology is a science, you have to adopt basic principles to build your theory. So when you decide to start a new science, when people launched hydrology. Why they did so? Because they had practical problems to solve, of course. And they decided then to study, probably they did it without really wanting it. But they started the science of hydrology, and like any science, you have to develop a theory. And to develop a theory, you need to identify basic principles. So, if one today wanted to start hydrology, what could be a basic principle? Well, you could think that hydrology is the study of movement of water, and the movement of water is dealt with by physics, because it's a body of mass that moves, and therefore you may start from physics. In fact, in hydrology and water resources management, two very important basic principles that are always satisfied are the conservation of mass and energy. So these are our basic principles for now. There will be more. But let's keep into account that if one asked you, what kind of science is hydrology? What kind of science is water resources management? Water resources management, we can consider it a branch of hydrology. And my first reply would be, it's a physical science, because some basic principles of physics are met. And if one asked you, how do you study the movement of water? You should say, first of all, by imposing the conservation of mass and conservation of energy. These are basic principles that are always met in hydrology, and therefore water resources management. So, coming back to my initial premise, it's important that I tell you that this is a mass balance equation, because you know that it's satisfied in hydrology. So, in a nutshell, I refer to a mass balance equation, which in my specific case becomes a volume equation, and this is the water balance equation. As I said, it's very, very simple. But it's simple, but not so simple. It's a differential equation. You see that you have a derivative here. It's a differential equation, which means if you want to solve it, because basically, what are the variables in which we are interested in this equation? Basically, we are interested in this variable, the output, which means the amount of water that we can take from the system. The input should be defined, should be known, and in our case, basically, is often rainfall. But then we are interested in what? We are interested in evaporation because it's a loss, but what we are mainly interested in is Q, which is the output, the amount of water, as I said, that we can take from the system. So basically we will try in this subject to derive, to make it explicit, Qt. Okay? And to do so, you need to integrate this equation. You can't use it in a differential form. You need to write an integral. And you may say, why that? It's simple if you think to the problem. It's simple to explain why you need to integrate it. Because there is an unknown in this system that you are considering, that is W. Water storage, it's an unknown basically. In some situation you can measure it, but it's an unknown. And this equation in differential form just tells you what is the change of W, but doesn't tell you what is the value. In order to get the value of W, and you need it, because if you want to solve this equation, you need the value of W. In order to get its value, you need to start from the beginning, apply at each infinitesimal time this equation, and reconstruct the whole story of this system. You have to start from a time t equal to 0, and then you draw the story of the system in time. And to do that, you have to use this equation many times. At each time step, again, this equation, which means integrating it. You can't use this equation in differential form. And so, you know, integrating a differential equation is always a bit of a problem. And we will see how to solve this problem. And basically, you have some knowledge of mathematics. You know that integrals can be computed numerically or analytically. And in the past, people used to try to compute the integral analytically because they didn't have the PCs. And you know, to apply a numerical method, you need to make a lot of computations. And now we have the PC, it's much easier integrating numerically with respect to analytically. But the PC, keep in mind, probably you don't know this very recent story. Until 1990, we didn't have any PC available. I had my first PC in 1985, but it was a very small PC that I used just for video games. And the personal computer, my first personal computer, I could have the opportunity to use one in 1990. And which means that just 20 years ago, we didn't have any opportunity to make, for instance, the exercise of tomorrow. 20 years ago, it was a dream. So people tried to compute the integrals analytically. Now, analytical methods are not so popular anymore. Why? Not because they are difficult to use. This is not the problem. The problem is that if you want to integrate a differential equation analytically, you have to simplify it, because otherwise it's impossible to solve. And therefore, in the past, people tried to use very simple models. They simplified the models because they needed to integrate them analytically. And they had the advantage that the solution was perfect. Today, we try to use more complex models, and because of course they are more detailed. But to do that, we have to integrate it numerically. This equation has to be integrated numerically. So we will see different options for doing that. In any case, when you integrate an equation, you need to specify an initial condition, a time t equal to 0, from which you start to reconstruct the story of your system. And also you need the boundary condition, which in this case are the inputs and also the losses. And also you notice already now that you have at least two unknowns here, which are your output variable, but also W, which means even if you had specified the losses and the inputs, it means that you can't solve this equation by itself. You need another one, at least another one, at least. So basically the model to solve this equation becomes a mathematical model which corresponds to a system of equations, not just one. Okay. So, A big problem in this equation, much bigger than integrating it, is defining what are the input. Even if you refer to the very simple case of rainfall, to define rainfall, to measure rainfall is very complicated. And therefore, we have to start from very far, having an idea of what is water resources availability, to focus on the orders of magnitude. And this is the reason why I said you should know how much rainfall you get where you live in a year on average. You should know that in Bologna, on average, you get about 1 meter of rainfall every year, on average. You should know that, because if you have an idea of the order of magnitude, of course, it's easier for you to solve a problem. It's a very typical problem in water resources management. People ask you, what is the input rainfall to my system? So, in the case of a lake, people would ask you, what is the input water flow to the lake? It could be rain, it could be a river that enters into the lake. To solve this problem is very, very difficult. And therefore we need to start from the orders of magnitude. This is why I started with this kind of slides. And in this case, of course, this slide doesn't tell you much. I told you that this is just an introduction. You just need for now to focus on the percentages. Okay. My introduction was a bit quantitative, because I wanted to clarify the very basics of the problem, because I would like we are engineers, and therefore I would like to deal with water resources management from the point of view of an engineer. So I want to focus on the theory, on the basic principles, and I will try in my lectures to make a mix between descriptive lectures, descriptive part of the lecture, and quantitative part. I will try not to be very heavy in my explanation. And therefore, let me now move forward with these slides that are a bit descriptive. The water cycle, we have to study this phenomena. And let me make an attempt to show you a video. I think I already mentioned on Monday to you that if you are interested in getting some educational material, the site of the United States Geological Survey is interesting. And also the site of the NASA has some interesting material for hydrology. And from the site of NASA, I got a video on the water cycle, which is nice, and I would like to show it to you. Let me see where it is. Here it is. Okay, this is, as I said, a nice video of the water cycle. You see the site is of the NASA. The energy comes from the sun. The sun favors evaporation. Evaporation, when the water vapor goes up in the air, and it gets into cold air, evaporation turns into condensation. And then you have the clouds. The clouds are moving from where you have a lot of evaporation, from areas where you have less evaporation. So basically you have evaporation over the sea, and then the clouds move from the sea to the lands. And once that they get over the lands, it's colder, especially because they got close to the mountains. And therefore, from the clouds you have the origin of rain. When the temperature decreases, you have the fact that air can take less water vapor in it, and therefore you have the formation of rainfall. And from rainfall causes the surface runoff, which means that water flows over the lands. But you have also groundwater runoff, because you have part of the rainfall that infiltrates into the ground and flows downstream in the underground. So you have a combination of surface runoff and groundwater runoff. And you have water storage in reservoirs. This is an artificial reservoir. And you also have the river discharge, which brings the water back to the ocean. So this is the water cycle that we already studied at the primary school. It's something that in principle we well know. Also you have some complications, a lot of complications, like precipitation in the form of snow, and then you have some water that is stored in the glacier, and etc. There are indeed a lot of complications. And we know this phenomena in principle very well. As I said, we were taught the water cycle in the primary school. But on the other hand, there is to say an important premise. If we look at the details, we don't know anything of it. Anything. So if we want to describe in the detail, for instance, what is the partition between surface runoff and groundwater runoff? So let's say that we measure rainfall and we want to predict the amount of rainfall that flows over the ground and the amount of rainfall that infiltrates. We can't do that precisely. We can get an idea, a very rough idea. We can't do that precisely. And I want to make you a more specific example. We make an hypothesis that rainfall partitions, I'm sorry for that, and just be patient for 10 minutes. We make the assumption that rainfall partitions into surface runoff and groundwater runoff. But we don't know if this is true. Basically, if you go in a catchment, if you go over a hill slope, even during a very heavy rainfall, you don't see any water flowing over the ground. You see the water flowing over the ground if you go to the roof of your house when it's raining. But if you go in a natural environment, you don't see water flowing over the ground, unless you really get in a very atypical situation. So basically some people question this interpretation. Some people, some hydrologists say that all rainfall infiltrates and the partition takes place underground between rainfall that infiltrates in the deep underground and rainfall that infiltrates in the very close underground to the Earth's surface. So this is another assumption that people do, because as I said, it's difficult to observe the surface runoff. But to describe this phenomena, we can't do that, because we tried in the small experimental basis, people try to dig some hill slopes in experimental basins, and they also provoked artificial rainfall to try to study how rain partitions, but the results of these experiments are contradictory. Of course, if you get a very impervious, meaning characterized by a very low permeability hill slope, then of course you are more likely to observe surface runoff. But it very much depends on the composition of the soil, depends on the structure of the soil. For instance, do you have a lot of worms that dig into the soils or not? The porosity of the soil is relevant or not? There are preferential flows in the soils or not? Preferential flow paths or not? For instance, if you have a lot of worms, it means that you have preferential flow paths which follow the tunnels that are digged by the worms. So you understand that the system is very complex, and this experiment gave contradictory results. So we can't really describe what happens when it rains, and we can't really describe the formation of the runoff. So we can't really say why water comes into the river. And another example that I want to give to you, there are some advanced theory that basically claim that the water that gets into the river during a flood, for instance, is not the water that just rained. These people say that the water that gets into the river is old water that was stored in the catchment a long time ago and stays there until you get an impulse of rainfall, and the impulse of rainfall provokes this old water reaching the river. But these phenomena are not known. So this is, from one side, on the one hand, it's an exciting perspective, because it means that if you want to make research in hydrology, or if you want to make professional activity in hydrology and water resources management, you have to make research. So this is exciting. You don't have just to study a book and follow what is written in the book. You have to use your mind. You have to make your idea on how a process evolves, and you have to make research in a way. On the other hand, of course, this is a bit depressing, because it means that at the end you have to design something, and your design is based on a theory that is still very rough and still evolving. So it's different from designing a beam. If you design a beam, you have everything that is very consolidated. You know how to do that, and you are fairly sure when you design a beam that the beam works. If you design a dam, you have to be very careful, because you never know what happens to that dam when it goes into operation. This is true. And for this reason, I always say that if I had a house that is located just below a dam, I wouldn't be so happy, because you never know. When you deal with water, you never know. Okay, let me go back to my sketch. And basically you see the same thing that I showed you in the video. You have evaporation from the oceans, and this slide just serves to you to get an idea of the processes, and you don't get numbers here. And so basically there is not much to say more than that we already said. You have evaporation from the oceans, and then you have the water vapor over the oceans that moves into the ground, etc. And there is one thing that I want to say that is not represented here. This is basically a pristine system without humans. Pristine means virgin in Italian, without humans.